Welcome to lesson 6, and this is Energy Diagrams 102. Now, to quickly review where we were in lesson 5, which should be the last video, we were talking about two different reactions, and those are diagrammed here on the screen again. On the left, we have the dissolution of NaOH into water. So we take some NaOH, we add it to water. If you're holding a glass in your hand that has this reaction in it, you're going to feel the glass is going to heat up. It's going to be like you're holding a cup of hot coffee or hot chocolate, and we call this an exothermic reaction. When you look at the energy diagram, this would be energy diagram 101, right? This is the basic diagram. We're going to extend upon this today, but you can see that we start out with the NaOH at a certain location on the energy axis here. We're going to call that E1. And then as the reaction proceeds, we eventually form the products. And they are at a lower potential energy that we'll diagram as E2. So the products here are at a lower potential energy than the reactants were. And one thing that we didn't talk about yesterday that is now a new concept is that the total energy in a chemical system is going to be the sum of the kinetic energy plus the potential energy. So now when we think about that issue in regard to this first reaction on the left over here, which is exothermic, since we're living in the world where the law of conservation of energy matters, so that's the thing to remember here, is that energy is conserved. So whatever the total energy is for this chemical reaction in total, that has to be conserved over the entire process. So when we look again at the reaction and we see that here's where we started with the NaOH at E1, and here's where we finished with the products, we're at E2, and you can see that the products have less energy, less potential energy compared to the reactants. Where did the other part of that energy go? And it was converted into kinetic energy, and that kinetic energy entered the surroundings, and literally the glass of water that had this reaction in it heats up because the potential energy that was lost by the reaction was gained by the surroundings, right? It was gained by the water in the form of kinetic energy, and the temperature went up. Now, when we apply the same idea to the endothermic option, and that was where we took ammonium nitrate and dissolved it in water to produce ammonium and nitrate, this is a reaction where we start out with the reactant, and this would be E1. And you can see where we finish after generating the products, we'll call this E2, that the energy of the products is greater than the energy of the reactants. So in this case, the products gained energy. So again, when we come back to this concept of the conservation of energy, where the total energy is the sum of the kinetic energy and the potential energy, since we had to lift up, right? We lifted, if I run a line straight out here, we had to lift the energy of the reactants to that of the products, right? So we had to like increase the amount of potential energy here from E1 to E2. The question is, okay, where did that energy come from? And what had to happen was that the kinetic energy of the surroundings had to decrease because that energy had to come from somewhere. And so in this case, if you were to add ammonium nitrate to a glass of water and hold it in your hands, you're going to feel the water cool down. And the reason that's going to happen is because the kinetic energy of the liquid is being utilized to lift these products, to lift up the energy of these products to the place that they have to be, to this new level of potential energy. All right. So the potential energy gain came at the cost of a kinetic energy decrease in the surroundings. So for the endothermic option here, we had a kinetic energy, I'm just going to do it this way, decrease in the surroundings. And for the option over here, let me change the color. In the surroundings, the kinetic energy increased because the products lost potential energy. So this was what happened in the surroundings. All right, now, there is yet another aspect to all of this business. And what I just got done going over, you may need to pause the video and think about it, or go back and watch this again and bring it to this point. Because now we're going to move on to the second point of this. So I'm going to call this A. And down here is going to be B. Okay, in the second part of this, what I want to emphasize at the beginning, so we're going to step back from this just a little bit. And what we're going to say is that there are two contributors of energy in chemical reactions. And we've been talking about one of them. So let's go ahead and list that out. Let's go ahead and list that out first. So number one will be the potential, or here, let me fix that. The difference in potential energy, I'm just going to abbreviate it as PE, between, and I'm going to abbreviate reactants and products. So it's going to be the potential energy difference between the reactants, which I'll call R, and the products. All right, and the second thing is, which we have not talked about, is what we call the kinetics of the reaction. Now, for all of you guys out there that like to have knee-jerk reactions, your ears better perk up right now, because I'm not talking about kinetic energy in the sense that we have been describing it. So what do we mean by the kinetics of the reaction? All right, in this case, what we're referring to is, let me put it this way. The energy of collisions that determine the time frame of the reaction. All right, so reactions have two things that are going on with them. There's going to be a potential energy difference between the reactants and the products, like the two examples that I have at the top of the frame here. And the difference in potential energy between the reactants and the products is independent of how long it took for the reaction to occur. And both reactions that I'm demonstrating here happen pretty fast in the laboratory, like within a minute or two. Sodium hydroxide and or ammonium nitrate dissolve in water. But there are other chemical reactions which have similar differences in potential energy between the reactants and products that could happen on the order of hours. All right, and there are other chemical reactions that happen on the order of milliseconds, and all of that stuff is being controlled by number two here. And I want to keep things simple. This is a basic chemistry class, so number two here is a more complex issue than just the way I'm describing it, but we're going to hold this to basically the energy of the collisions, even though there's some other factors that are involved in this that determine how fast the reaction is going to happen. So number one and two are distinct things. Number one has nothing to do with how fast the reaction is going to happen in the real world, and number two has nothing to do with the potential energy difference of the reactants and the products. Number two solely has to do with how fast the reaction is going to go. So in order to finish the video and to complete the energy diagrams, what I'm going to do in here is enter in the factor that involves the kinetics, and I'm going to deliberately use a different color. So there's going to be a hump in here that's going to look like that. And similarly, there's going to be a hump for this one too. And I'm just drawing the hump in arbitrarily. But now let's go ahead. It is a different color, so I want to emphasize the fact that what I just drew in here has nothing to do with the potential energy difference between the reactants and the products. What it has to do with is how fast the reaction is going to go, or the kinetics. So let me label that. Do not confuse this with kinetic, the kinetic energy issues that we've been talking about. All right, and let's see, where am I going to put it on this one? I think I can squeeze it in like this. So this is the kinetics. Has to do with the speed, how fast the reaction is going to happen. Now, there's a special quantity here at the top of this curve, so if I was to draw a line over to the top, you can see that we're able to indicate another form of energy, and we're going to call this E sub A here, and there's going to be a similar value for this one. This is called E sub A. All right, and this is what we call, I'm going to have to put this over here. So I'm going to draw a colored box here to put the definition in. I know this is cluttered, but this is what it is. Life is not always really easy. All right, so here we go, E sub A. This is what we call the energy of activation. All right, or activation energy. The term is used both ways. I can't help that, it's just the way it is. So activation energy, both of them mean exactly the same thing. It just depends on the darn textbook that you're reading. Activation energy. All right, and this is the energy that is required to initiate, I'm going to change the color for that to emphasize it, to initiate the reaction. It's all about initiation. You got to get it started somehow. And I'll underline that, initiate the reaction. All right, so this is the E sub A. So if you think about it a minute, if you're going to go to start a campfire, you're going to have to light a match. What does lighting the match do? It provides the initiation energy to get the fire going, right? Without the initiation, the little flame provided by the match, you're not going to have a campfire. And what that little match is doing is it's providing the energy to basically activate or initiate the reaction. So the E sub A would be drawn off of this line to this point. All right, for this reaction. And the E sub A in this reaction is going to go from here to there. Now, last thing before I close the video out, we'll come back over here on the left, and some of you might be wondering, well, this reaction isn't warm to start with, so where is the energy coming from to actually get the amount that you need, the E sub A, so that the reaction happens? Where is that coming from? Well, okay, this reaction is started in water that is at room temperature, and so kinetic energy The kinetic energy that's available in the liquid is what starts to drive this. And then the next person might want to argue, well, then why doesn't it cool down, Dr. Pete? Well, because this is an exothermic reaction. So once this reaction begins to happen, it starts producing lots and lots of energy, which just cycles back to initiate the next round of reactions. So this is sort of like a chain reaction is how it works. In terms of the reaction over here on the right, the kinetic energy to get this thing initiated indeed has to come from the liquid, and it's going to contribute to the overall cooling of the mixture. All right, and with that, I'm going to go ahead and close the video. Again, if you're having a hard time understanding this, you need to pause the video, think about what I'm talking about. You may need to go back and watch it over again, and you might have to watch it more than, maybe 2 or 3 times over again. In any case, I'll see you pretty soon on lesson number 7.